mentioned in the previous lecture, we are going to talk about subspaces of vector spaces. These subspace, why we need to talk about subspaces, or why you want to consider subsets of a vector space which can behave as another vector space. It may not be clear when you study this. You might be seeing that this is, in Hindi we would call it jabardasti, means you are just forcing a concept down somebody's throat. It is not really like that. This idea of subspace would come in, as you will come and see in the next lectures. This idea of subspace will become very important, that certain type of subspaces play a more important role than the original space. So, we will have it very soon. So, that will be very true with certain kind of matrix spaces, matrix vector spaces. We will talk about that very soon. So, if you have a subset, say U of a vector space V, then you want to see when can this subset become a subspace. To what makes a set a vector space? It must have vector addition operation, it must have scalar multiplication operation. Both of them you can say that I can borrow from V, I can borrow the same operations from V, but just by borrowing them, borrowing that operation, you cannot make U the subspace. You can say, oh, you can also borrow the, this additive identity and additive inverse, means 0. I can borrow from V and just attach it to it, and the same operations. In most cases, we do take the same operations, but it becomes a subspace induced by the same operations, that you have borrowed those operations from V. If 0 belongs to U, if whenever alpha is in F and A is in U, alpha A should be in U, it cannot be outside U, because that is an important property, the closure property of a vector space, that has to be maintained. Once that is maintained, every other property will follow. If U plus V is element of U, then U and V element of U, then U plus V should also be an element of U, cannot be some other element of V which is not in U. So, you have you have possibly borrowed actually you have borrowed the same operations from V for U, but you have put in the restriction that needs to make this a vector space, and that restriction is the closure property. Once the closure property holds for you, everything else will follow. That is the guarantee that we can give, and you can check the guarantee. Once lecture 4 is over, or detailed you can say assignment would be put up on the Hello MOOC kit. So, do not worry about that. Now, let us see what you mean by subspace. So, if you take the xy plane and you have the origin 0 0 and you have the x coordinate, y coordinates, what are subspaces? These are actually lines passing through the origin. That is a subspace. The 0 element itself is a subspace. It is a 0 dimensional subspace. The lines are 1 dimensional subspace. If the line does not, moment the line is not on that not passing through 0, that will not be a subspace. Moment to translate it off a bit, for example, here, why it is subspace? Because you take any vector V, which is here, say, you will scalar multiply, it will remain here. You take any two vectors here on this part, this way or both this way, if you add them also, they will remain on U. That is why it is a subspace. So, consider all x y element of R2, you can write it transpose also. I do not know, I have sometimes I have written it in this case, sometimes I have moved it out. See, when you write in terms of sets, you actually write the things in a row vector, but they should actually be formally should be written as a column vector, because we have said that vectors would be always written as column vectors, column of coordinates. But sometimes in mathematical writing, those who are involved in mathematical writing for so long, sometimes you keep on what comes naturally to you. because I have when I do my other research and other when I maybe optimization, my subject which I love, and that when something I usually write it like this x, y naught 2 such that so and so happen. So technically I should write a transpose, but I have just removed it. In the others later on I have written the transpose so that I do not lose the sight of it. For example, if I have pushed it up now, moment why it is not a subspace. So set of all x y such that x plus y is equal to 1. So it is the line passing through 0 1 1 0. First of all, 0 is not in u1. So immediately 0 is not there, so it cannot be a subspace. In fact, if you take two elements 1 0 and 0 1 and add them up, they will give you 1 1. They will be the coordinate 1 1. It's here. It's not lying on u1, so it is not a subspace. So if you take alpha equal to half, say, and then take half of this, it will be half of 0. Half and 0. Why 0? It's half and 0. So half plus 0 is not equal to 1, so it is not also on the subspace. 1 plus 1 is obviously 2, not equal to 1, so both are not in the subspace. So whether I do vector addition and whether I do scalar multiplication with this simple vector 0 1 or 1 0, these two vectors, this and this, it's clear that it doesn't follow the requirements of a subspace. So if you just move it off from 0 in R2, those lines are not subspaces. Only if they pass through 0 they are subspaces. It's just kind of interesting. Now consider the space CR of all continuous functions on R, right? So now let dr denote the space of all differentiable functions on R. So set of all differentiable functions is a part of all continuous functions, set of all continuous functions on R, because every differentiable function is a continuous function, but the reverse is not true. And everybody would understand calculus much better if they know at the very outset that every continuous function did not have a derivative. So this is the proper subset. So I have given this, I have not equated it. There is no equality here, that there could be a possible equality. No, there is no equality. So is dr a subspace then? The answer is yes, because the 0 function, which is f t equal to 0 for all t, is differentiable. 0 function is obviously differentiable, and if f and g both are differentiable, then is f plus g also differentiable? The answer is yes, because you can easily compute its derivative, because the derivative of f plus g is nothing but the sum of the derivative of a at any point t on R is sum of the derivative of t plus sum of the derivative of g, the sum of the derivatives of f and g evaluated at t. So f plus g, we can also compute the derivatives once f and g are in dr, let us say the space of differentiable functions, f plus g is also there. Now you take lambda f dash of t, lambda f is the function now. So is it, if f is differentiable, is lambda f differentiable? Lambda f dash of t, by very basic definition, when you say, again I told you this f g, now these are abstract things. Now when you make f plus g, how do you say what is the meaning of f plus g? The only meaning when functions are concerned, these machines, these functional machines are concerned, is that you show how they act on their domain. That's the way you show how what are their properties, what are their nature. So lambda f of dash t, you can just compute out automatically, is same as lambda of f dash t. So hence this is a subspace. Now there are some important aspects of subspaces. Now you can say, okay, let us go back to this example. You see, the space of differentiable functions on R is a subspace, and is an important subspace. These are the type of functions which are very, very important in other aspects of analysis. So derivative is a key idea on which calculus is based. So this subspace is important. The whole, more important than the whole space is that subspace. Just having a continuous function and not having some more properties may not always be a good idea, right? So that's the kind of thing. So let us look at some properties of subspaces. So if I have two subspaces u1 and u2 of some vector space V, then the union need not be a subspace, but the intersection is a subspace. Let us see how it is. take u1 is set of all vector, I should write as column vector. So, please forgive me, x y such that or you can write it like this also, does not matter, it is you understand. Once you understand the idea, that okay, fine. So, you might say, okay, what is this guy telling? Okay, you can write as row vector, you can write as column vector. No, because I would always write just for the, because this is the way I am habituated in writing, but in my mind I know that I am writing it as a column vector. So, I am not writing x y transpose basically. It does not matter if you write it as row vector also, but when finally when you will walk through it, when you will just separately write them, you will write them as column vectors. So, I am telling that to write everything as a column vector because that is a tradition, because we are coming through this idea of column space of a matrix. We are looking at everything to columns. You could have looked at everything to rows, but handling rows is slightly difficult compared to columns, because column allows us to express the multiplication of a vector with a multiplication of a matrix with a vector as a linear combination, and that is why this column representation becomes important. That is the key idea. So, okay, let us take that out and let u1 and u2 be two spaces, set of all x y where y equal to 0, which is the x axis, and u2 is the y axis. So, if you take the x axis and y axis in the plane R2, V here is R2, then the intersection is 0. So, 0 is a trivial subspace, obviously a subspace, nothing else to do. But you take the union, then what does it mean here? Either x is 0 or y is 0, both is 0, both 0 happens at 0 0, otherwise either x is 0 or y is 0. Now, you take 0 1, 1 0 is in u1 and 0 1 is in u2, and as I showed you earlier, there are sum, this should also be written transpose because I have written transpose 1 0 plus 0 1 is 1 1, which is not in u1 union u2, because the 1 1 does not lie either in the space u, x axis, nor on the y axis, that is it, it is inside. So, u1 union u2 is not a subspace. What is important for us is to talk about sum of subspaces. Here I am taking you to a different kind of idea, which we will call the direct sum of subspaces. Those who have seen the lectures of Gilbert Strang would see kind of Gilbert Strang's talks about 4 fundamental subspaces in Rn. And there very tacitly he uses the idea of direct sum, though he does not give a more detailed discussion on it, but because those who would read his books or who would read or see his lectures, which is very important, that I want everybody in this class should at least have a look there, would do well if know about what is a direct sum of subspaces. So, this direct sum is a very key idea, and that idea has to be understood very well. Without understanding this very well, a lot of things in linear algebra would not become clear, because linear algebra essentially is a game played with direct sums of subspaces, and that comes in at many places, even in things like quantum mechanics it is used. So, let us be relaxed and let us understand. Suppose we have subsets of V, we are not talking about subspaces, we are telling these are subsets. Now, what is the meaning of adding them up? This is called the Minkowski sum, after the famous mathematician Hermann Minkowski from Switzerland, who was also a teacher of Einstein. So, in Zurich, u1 plus dot 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 um, this addition of this subset means any element of that new set is of the form u1 plus u2 plus dot 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 where each ui comes from u1 u2 So, the first position u1 has to be filled with some element from capital U1, the second position some element from capital U2, third position from capital U3 and mth position from capital UM, and you have to add them up. So, you can make all such possibilities, many possible additions are there. In fact, if you have U1 in general, it will be infinitely, uncountably infinite. It will be infinite and uncountably infinite actually, unless these are have only finite elements, but which usually we would not consider, because those are not the fun sets always. So, then what would happen? Then U1, so these there are so infinite possibilities are there. So, that will form a new set. So, you will make all possible types of vector additions, and we will take those elements up and form a new. So, all these elements would finally remain in V. So, U1 plus U2 plus UM would be an element in V. So, if you have U1 and U2, there are two vectors, two subsets of R3, x00 and 0y0. So, what does it mean? This is the x axis and the y axis in R3. So, if you add these two, you will get the xy plane in R3. You will not get R3, you will get the xy plane in R3. The xy plane is actually a subspace. So, now the question is, this example is from Sheldon Axler's book Linear Algebra Done Right, 3rd edition 2015, and also another proposition. So, now the question is that these two are subspaces, because in R3 the planes passing through 0 are subspaces, all the lines passing through 0 are subspaces, that is it. And the whole space is obviously a subspace of itself, we do not have to say, and the 0 0 0, and also the empty space is also subspace, there is an empty set, that is just obvious. So, I sometimes do not, I do not sometimes like to be so mathematically correct that say, okay, the whole space is also a subspace of itself. That is so obvious, you do not want to speak of them. Look at things which are not the whole space, not the empty set, those are the interesting subspaces. So, it is better to talk about interesting things, but do not, if you want to stick on very strongly to the mathematical eruditism or mathematical logical you know cleanliness, then you have to say that the whole space is also a subspace, the empty set is also a subspace, kind of things like that. See. So, if I say 0 is a subspace naturally, but it is trivial, you do not really have much to do with it unless showing it in such examples. Now, here these two subspaces added up to a subspace, but it may not be the case that things may add up to a subspace, right. That is the key thing. Suppose I am adding up x axis and y axis, then obviously I am not getting subspaces, right. I may not get subspaces. So, that is what I am trying to say. When if I get so if I so if I add up the x axis with some other set, other vector, I might not always get a subspace, that is the idea. So, if I have so if you take if I take two sets which are not subspaces, right. So, then for example, I take the set of U1 is a set of all x plus y equal to 1, and then I take the set of one is x axis, one is a y axis. Then if I take their sums, then I may not get back elements which are within the union of these three or something like that, or the sum may not be a subspace. So, that kind of thing. So, unless these are subspaces, the sum may not be a subspace, that is the whole point. So, if these are subspaces, the sum is a subspace. So, let U1, U2, UM are subspaces of V, then U1 plus dot 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 UM is the smallest subset containing U1, U2, UM. So, here so proof is pretty simple. Now, each of these UI is contained in this set, because since each of these UIs are subspaces, zeros are elements there. So, 0 plus 0 only in the UIth place I put an element, some element of UI plus 0 0 0, that is also in U1 plus U2 plus UM. So, I keep all the things, all the elements 0 and only keep elements from UI in the ith place. Then the elements that are formed are only elements of UI, but by the definition they are also elements of U1 plus U2 plus UM. And as a result of that, we can say that each UI is contained in this sum, right. So, here one has to be very careful that when I am summing up subspaces, do I get a when a u1 plus u2 plus um, will that be a subspace? That is a key thing to keep in mind. So, that when u1 plus u2 are subspace, the sum will appear to be a subspace, but if they are not subspaces, the sum may not be a subspace, it can be just a subset. Because what happens if u1, u2 are subspaces? So, suppose I take any element of u1 plus u2. So, u1 would be in u1 and v1 would be in v1. So, u1 plus v1 would be in. So, if I take any subspace in two elements in u1 plus u2, u, v and w. So, v can be written as v1 plus v2, where v1 is in u1, v2 is in v2, and w can be written as w1 plus w2, w1 is in u1, w2 is in u2. Now, if you sum them up, so what you will get? You will get, when you sum sum these to v plus w, you get u1 plus you will get u1 plus u2 plus w1 plus w2 again. So, u1 plus w1, because these are elements in u1, they sum up to be an element in u1, and u2 plus w2, if you sum them up, they would become elements in u2 because they are subspaces. So, if you basically the element v plus w is an element in finally u1 plus u2. So, if I am summing up subspaces, the sum of these two sets are not just a subset, but a subspace. So, this is a very important thing to remember. Now, it is a this should be not smallest subset, is the smallest subspace containing u1, u2, um, because ultimately when you have u1, u2, um as subspaces of V, then the sum is also a subspace. So, if there is any other V dash, any subspace of V which contains u1, u2, um, then it must contain u1, u2 plus um by the definition of the subspace. So, because if it contains u1 and if it contains u2, then it is a vector space V. So, any element of u1 is also an element of V dash. If element of u2 is element of V dash, element of u3 is element of V dash, and if I add them up, all of them are lying in V dash. So, u1 plus u2 um, that element is in V dash, that is it. Because when you add elements from V dash, you will get in V dash, because V dash is anyway subspace. So, u1 plus u2 plus um, if it contains u1, u2 ... must contain u1 plus u2 plus um by the definition of a subspace. So, u1 plus u2 plus um is the smallest subset containing u1 plus u2 plus u2 ... um. So, for any subspace that contains u1, u2, um, it must contain u1 plus u2 plus um. So, there cannot be any subspace smaller than u1 plus u2, smaller than u1 plus u2 plus um, which contains u1, u2 and u1, u2 ... um. So, here we say we leave it to the reader to show it as a subspace. Just for two spaces I just gave a discussion, which may or may not be clear to you, which means that what you do, you take two elements v and w from u1 plus u2. Now, you want to show that v plus w itself is in u1 and u1 plus u2. So, v is in u1 plus u2, w is in u1 plus u2. Because v is in u1 plus u2, you can write it as v1 plus v2, where v1 is in u1, v2 is in u2, and w can be written as w1 plus w2, where w1 is in u1 and w2 is in u2. Now, you add that v plus w. So, what I will get? v1 plus v2 plus w1 plus w2. Now, using the commutativity property, you can write v1 plus w1 plus v2 plus w2. Now, what is V1 plus W1? Now, by the associative property, you can do it, add them separately. V1 plus W1 is what? V1 plus W1, V1 is an element of U1, W1 is a element of U1. So, V1 plus W1 would give me element of U1, which we call say V dash. And here you have plus also the vector W1 plus W2. W1 is the element of U2 and W2 is the element of U2, because that is a vector space. You add them, you will get an element of U2. So, what is then, which we can call the W1 plus W can call W dash. So, V dash is the element of U1 and W dash is the element of U2. So, V plus W is V dash plus W dash, which is a element of U1 plus U2. So, which means V plus W is also element of U1 plus U2, that is it. So, again you take the x axis and y axis. Observe that you take any element, add them, and you take any x y, and you can always write it as x 0 plus 0 of y. And for every x y, there is this unique way of writing R2, x y as a form x 0 plus 0 y. So, here what we do, we are telling R2 is a kind of direct sum of U1 plus U2. I am just using the terminology direct sum right away. We can talk about it later on, what is the direct sum and what in a more precise way. What it means that given any element in R2, it can be expressed as a sum of two vectors U1 and U2, where U1 is in small u1 and small u2, that is given any w in R2, w is equal to u1 plus u2, small u1 plus small u2, but small u1 is the element of capital U1 and small u2 is the element of capital U2, and this representation is unique. There cannot be any two other vectors u1 dash and u2 dash belonging to capital U1 and capital U2 such that w is u1 dash plus u2 dash. It is not possible. Then we say that if that is not possible, then we say u1 plus u2 represents a direct sum of R2, or rather R2 is a direct sum of U1 plus U2. So, R2 in this case is the direct sum of the x axis and y axis. So, let us introduce this key fact. So, let U1, U2, Um are subspaces of V. Then we call capital U1 plus U1 plus dot 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 plus Um. Then we call the U1 plus dot 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 plus Um a direct sum. I missed the term. Then we call U1 plus U2 plus Um a direct sum if each V in U1 plus U2 plus Um can be written in a unique way as a sum of elements of V1, V2, Vm. So, if V is equal to U1 plus U2 plus Um, then Ui and Ui is element of capital Ui, and then this is the only way to represent V as a sum of elements of U1 plus U2 plus Um. So, that is so then we call U1 plus U2 as a direct sum. Here the term direct sum would come. So, we will call the sum of some subspaces the direct sum if for any element of U1 plus U2 plus Um there is only one way of writing any element as a sum of U1 plus U2 Um, only with one pair of representation. There cannot be more than one pair of representation, that is it. One way, any other way of representing. So, the direct sum comes in many ways. It is symbolized like this kind of a medical type of symbol, cross, red cross, or in this way. So, here you look at xy element of R2, that is what I just told you, that is a direct sum. So, these are subspaces x axis and y axis, and there is a unique representation. So, R2 can be written as a direct sum of U1 and U2. So, here is another example of Axler. So, x y 0 in R3 x and 0 0 z in R3. So, these are all subspaces, these are all passing through 0 0. So, these are all subspaces of R3. R3 can be written as U1 direct sum of U2, because x y z can be written as x y 0 plus 0 0 z. There is only one way of doing it. There is no more than one way of doing that thing. So, that is what we have to keep in mind. So these are very important thing, you have to go on practicing it. Suppose I can write this R3 has a sum of 3 subspaces, right, direct sum of 3 subspaces. I can write U1 as x0 0. So, this is not an example of axolot, this is just I made up while writing. So, U2 as 0 y 0, this is also subspace, that is this is the x axis in R3, this is the y axis in R3, this is the z axis in R3. So, here what was the subspace? Here the subspace was the xy plane and the z axis. So, you take any element in the xy plane and add it with the element of the z axis, you will get one you will have a unique representation of element in R3. So, here what I do, I again decompose it further. Basically, I decompose the z axis itself, the xy plane itself as into these 3 subspaces. Now, R3 is the union of U1 plus U2 plus U3. So, Rn in general can be written as a direct sum of these axes subspaces where Ui consists of elements like this. So, it is an Rn, it's not R3, sorry, it is mistake. Rn where Xi is element of R. There is a lot of printing mistakes here which I will have to correct at a certain stage, but students please correct it here. Now, suppose I do not take this kind of x axis and y axis, but suppose I take U1 hat as my x axis and U2 hat is the line y equal to x, all the coordinates are of the form xx. Is R2 a direct sum in this case of U1 and U2? Can xy be written only in a unique way using unique elements of the x axis and that is U1 hat and the subspace U2 hat which is consisting of xx. In fact, indeed yes, any xy can be written as x minus y 0 plus y, because if we add these two vectors x minus y plus y is x and 0 plus y is y. So, it will give me xy. X minus y 0 is U1 is in U1 because it is of the form x0 and this is x is in some element, any number from R, some real number. So, this is a real number. And what is yy? Yy lies in U2 hat. So, this should be U1 hat and U2 hat. So, this is so yy is here and xy0 is here. So, there is only unique way of representing this, there is no other way of representing this. If there is any other way of representing, they must all coincide. You can see it very well because these xy are given fixed number. Given this xy, there is no other unique way of representing this as a sum of element from here and a sum of element from here, there is no way. So, R2 actually is U1 hat, U2 hat. This happens when you keep on writing, you sometimes forget the symbols that you have been changing to just make things look different. These are the following theorems we mentioned from Axler, which we will not give a proof here, the proof is very simple, so we will not prove. So, we just mention them and the student should try to think about them, rather can work out the simple proof. Suppose U1, U2, UM are subspace of V, then it actually gives you a criteria under which condition you will always have a direct sum, right. Let us see. Then given U1, U2, UM are subspaces of V, what are the relation between U1, U2 and UM so that their sum is actually a direct sum? Their sum is actually a direct sum. They can be considered as a direct sum, right. That is, every element can be represented in a unique way, and this has to do with the 0 element. If the 0 element can be represented in a unique way, that is 0 can be only written as 0 plus 0 plus 0 plus 0, then only you can call U1 plus U2 plus UM as a direct sum. So, suppose you have subspaces U1, U2, UM of V, then U1 plus U2 AM is a direct sum if and only if the only way to write 0 is the sum U1 plus U2 plus UM with each UI equal to 0, because if you take U1 equal to 0, U2 equal to 0 and small um equal to 0, if you sum them you will get 0 naturally, 0 plus 0 is 0, just go on, it will be 0. So, this is one way of writing 0. If this is the only way of writing 0, because there are no other way of writing 0, then only U1 plus U2 plus UM can be considered as a direct sum. Let us see. Now, if you have two subspaces only of V, then U1 plus U2 is a direct sum if U1 intersection U2 is 0. Now, you see, for example, in this example, which is not your familiar x axis and y axis, here u1 hat intersection u2 hat is 0. This is the only intersection they have, there is origin 0 0. 0 0 is the only intersection they have, the 0 vector of the space. So, then u1 plus u2, if you do the summation of elements there, they will become a direct sum. So, if you add elements from there, they would indeed become direct sums. And if you start adding elements from here, for example, if you add x0 plus xx, it will become 2x or if you add an element say x plus y minus y minus y, so it will give you x minus y in that way. So, if you add any two elements, there will be the sum would always give a unique representation. And the vector that they will finally make when you add the two elements would be uniquely represented only in terms of these two elements that you choose from u1 and u2, because their intersection is 0. This is a very powerful result, I love it actually. If u1 and u2 be subspaces of V, then u1 plus u2 is a direct sum if and only if u1 intersect and u2 is 0. It is an if and only both way characterization, and that makes it so beautiful and powerful. So, with this I end this lecture and hope this is a very important discussion that we are having, and the next chapter would be important discussion, and then we will go back to our familiar handling of matrices. We will just talk about how to solve equations and kind of things, and at the end of the course on linear algebra we will really talk about a bit about convex sets, because certain things economists must know about Carathéodory theorem before, if there is time of course, before moving on to an analysis, which is also important that we have to do. Okay, thank you, all the best for today and have a good evening.